Welcome to Math 31. We are in Chapter 7, looking at trigonometry, and today we start with some derivatives of sine and cosine. And then we'll apply all those rules, product rule, quotient rule, chain rule, etc., that we learned back in Chapter 2. So here our first question, called an example, but I'll give you some time, I think, once I get you set up. We want to use the definition of a derivative to figure out what's the derivative of sine x. Well, the definition of a derivative, as you will recall, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And here I've substituted the x plus h and the x into the sine function. So what I would encourage you to do is see if you can figure out what this is going to be equal to. Let me give you a hint. This sine of x plus h is a sum of angles, and so you can use a sum identity from your formula sheet to expand this out. So why don't you pause the video at this point, expand this sine of x plus h using that sum identity, and see where that takes you. You can pause the video now, restart it when you're stumped, or when you just want to see what my process is. All right, here I have applied that identity. Sine of x plus h is sine x cos h plus cos x sine h. Now, h is a little bit sketchy when it comes to trigonometry. We haven't experienced it, but there's something that's known as a hyperbolic sine or hyperbolic cosine, and it's represented with cos h, kind of all as part of the operator, and then what we're operating on comes after that. You wouldn't know that yet, but just a bit of information for your future. Well, what do we do from here? Well, as I look at this, I see that I have a sine x and a sine x, and as in, find a marker, let's go yellow. So I'm looking at this sine x here and that sine x there, thinking, oh, that could be a common factor that I could pull out. Why would I want to pull that out? Well, they don't have any h's with them. And so if I was to separate this limit into a couple limits, I could take that right out in front of the limit. And another thing I notice is that here, oh, there's a sine h over h kind of mixed into everything. And if I can separate this piece out, then I'll be able to use this fact that the limit as h approaches 0 of sine h over h will equal 1, which we learned in 7.1. So that's kind of where we're going to go with this question. Here we go. So you can see I've separated this into two limits. So the two parts that had the sine x's I grouped together in the front, and then this middle piece I put afterwards. So I broke this one big fraction into two smaller fractions, and I can take the limit as h approaches 0 of both of those. And you'll notice I have in red the sine x. I can pull that out as a common factor, put it in front of my limit. Same thing with the cosine x in the second limit. Here's where that takes me. So I have the sine x out, the cos x is out, and then I have this cos h minus 1 all over h, and you'll recall from 7.1, we could use a Pythagorean identity if I multiplied by the conjugate of the numerator. So that's what I'm doing, and over here, there's that sine h over h. That is going to equal 1. Now here, as we look at this, after I've multiplied those conjugates together in the numerator, this is the opposite of what I'm looking for. So this isn't equal to sine squared h. This is equal to negative sine squared h. So that's what my numerator looks like there. Well, now that I have those sine squared h's, let me just pause for a second. Sine of h As h goes to 0, this goes to 0. This h also goes to 0, so I'm getting 0 over 0. That's why I have to go through all these different contortions to try to manipulate this and get rid of those 0 over 0s. But this sine squared h, I can separate that to two sine h's. So I have a sine h over h, the negative sine h, so I'm keeping that negative with my second one, over cos h plus 1. And we know this limit, again, is going to equal 1. And the second limit, sine of 0 will be 0. Cos of 0 is 1, plus 1 is 2. So I have 0, well, negative 0, over 2, which is just equal to 0. It's not a 0 over 0, so I'm able to plug the h in to evaluate, and that's where this 0 comes from. Which means the derivative of sine x is cos x. We could go through all the same similar kind of steps to determine the derivative of cos x, but I'll just tell you. Derivative of cos x is negative sine x. These two derivatives are what we will use throughout the rest of this lesson. And here we have some examples. We want to determine dy dx, the derivative. If you want to use y prime, that is fine. We're just saying we're looking for the derivative. Well, I know the derivative of cos x. I know the derivative of sine x. I have a product. I need to apply the product rule. So my first function, cos x, times the derivative of sine x in red, plus my second function, sine x, times the derivative of cos x, which we discovered was negative sine x. Well, we can simplify that a little bit. Cos squared x minus sine squared x. We could stop there, but when I look at this, I think there's an identity, which is cos 2x. So this is one of the double angle identities for cosine. Question number 3. Now I have the sign of a product. So in question 1, I needed the product rule. Now this product is inside my sine function, so I'm thinking chain rule. So I do the derivative of the outside function, derivative of sine is cosine. Keep the inside unchanged, pi times x, times the derivative of the inside, which is just the coefficient of x, which is pi. And we could leave it like that, but often those coefficients are written in front of the trig function, like this. Question number 4. Cos x squared. Well, I could think of this with the product rule or as a chain rule. So I think I'll think of it like a chain rule where I have the cosine x as my inside function, and then x squared is my outside function. And so chain rule says I bring the 2 down in front. I keep the inside function unchanged, subtracting 1 from the exponent, so that's why I have a 2 cos x, times the derivative of the inside function, and that's the negative sine x. So again, as we think back to chapter 2, this is the f prime of g of x, and this part here is the g prime of x. Question number 5. So notice the similarities between 4 and 5. Both of them have squared, both of them are cosines, but there's a difference. In question number 5, that power is inside the function. Number 4, the squared was outside, the whole function. Number 5, inside only applying to the x. Again, I will need a chain rule. My outside function this time, though, is cosine. Derivative of cos is negative sine. Keep the inside unchanged, times the derivative of the inside function, which is 2x. And then I'll just rearrange. On to question 6. Now I have a trig function inside another trig function. this can only work in radians. Remember, a radian is a ratio of two side lengths, so a cosine function as input can only take a ratio. No, it can take an angle. And the output from this sine function is going to be a ratio. So for this cosine to take something as input, as a ratio, it has to be operating in radians. Well, we don't have to know that to do this question, but again, we have outside function, inside function, and we apply the chain rule. Derivative of this cosine is negative sine, keep the inside function unchanged, still the sine x, times the derivative of that inside function. And that's it. End of question 6. Number 7. Oh, yay! We have two y's, one inside the cosine function, one outside the cosine function. We need to use implicit differentiation. If you thought we were done with implicit differentiation, we're not. Ha! There we go. So we take the derivative of the left side, dy dx. Derivative of cosine is the negative sine, keeping the inside unchanged, times the derivative of the inside is a product rule. So first times the derivative of the second, plus the second function, y, times the derivative of x, which is just 1. You'll remember for these questions, we want to isolate the dy dx. So we need to take this negative sine xy and distribute it into this bracket. Common mistake is forgetting to do that distribution. So we're taking all of this and we're going to multiply it to the x dy dx and also to the y. Really important to remember because it's easy to forget. So here's what it looks like when we do that distribution. So the negative times the x times the sine xy times the dy dx, and then that second term. We want to collect the dy dx's all to one side of the equation, and then factor out that common factor of dy dx. And remember here where we just had a dy dx, when it's factored out, we still have this 1. And then we can divide the square bracket over to the right, and we've found dy dx using implicit differentiation. Well, there we go. Pile of examples. That sets you up. You know all the rules. Now we're just applying them to sine functions and cosine functions. So quite a few check your understanding questions for you to try here. So why don't you pause the video at this point and then restart when you're ready to check over some of my answers. There's my answer for question number 8. Pretty straightforward, I hope. Question number 9 is a little more complex. So here's what I got. So my outside function is something to the exponent 5. So I bring the 5 down in front, subtract 1 from the exponent, and that's why I have that exponent of 4 up here. So the 5 is brought down in front, keep the inside unchanged, and I still have the sine of that inside. It's part of the inside function. Then I go to the next layer in, which is the sine of the something. Derivative of sine is cosine, keeping the something unchanged. One more link in the chain is the derivative of this inside part, which gives us the 6x. So it's like a chain rule with three functions in composition with each other. Next page. This time we'll want a product rule and a chain rule. So here's what I get. First function times the derivative of the second. So my derivatives are in green. Plus my second function, unchanged. Oh, remember, when I do the derivative of sine x squared, Derivative of something is cos. Keep the x squared unchanged times the derivative of x squared. That's the chain rule part. And then I just rearrange things a little bit for my final answer. There's a common factor of x squared we could take out, but no real point at this stage. Question number 11. Implicit differentiation again. Here's what I get for my first line. Derivative of cosine of something is negative sine of that same something, unchanged, times the derivative of the inside, which is 1 minus dy dx. On the right-hand side, again, I have a product. So first function times the derivative of sine x plus the sine x times the derivative of y with respect to x. Again, we have a similar challenge on the left side here, where this whole trig function needs to be distributed to the 1 and also to the dy dx. Which leads us to our next line and everything else. Oh, look at all that information. Let's hide a bit of it. Here we go. So here I've distributed in. This blue part multiplied by 1 is still the same blue part. The blue part times the negative dy dx. Well, the blue part was negative times negative gives me a positive sine x minus y times dy dx. Right side is unchanged. Next, I'm collecting my dy dx terms on the left, my non-dy dx terms on the right. This sine x dy dx gets subtracted over here, and this negative sine x minus y gets added to the right-hand side. Factor out the dy dx and divide to get our final answer. Question number 12. We want a second derivative. Quotient rule this time. Ooh, we haven't done a quotient yet. So, low d high minus high d low. Square the bottom and there you go. When we do a little bit of cleaning up from this, here I have a sine x times sine x squared. And when I distribute here the negative and the cos x into the bracket, I'll get a negative cos x. I put that here in blue. But I'll also get a positive cosine squared x. Notice I highlighted that in red, Pythagorean identity. That is equal to 1. How do you know when you should apply an identity? Well, keep your eyes open, especially in this case where we want to find a second derivative. We want our first derivative to be as simple as possible. And then even as you look at this, you could see, oh, you know, I could rewrite this sine squared x as 1 minus cos squared x, factor it, and I could actually cancel out a 1 minus cos x. So that would be an option. I chose not to do that. Instead, I just did the derivative from here. And again, low d high is in black, minus high d low is in black on the right side. Square the bottom, there you go. And then I factored out a sine x, and I looked at all this stuff left in the brackets here. Ooh, and I just kept going. So here's what I did. I have a sine squared x here. I have two cosine squared x's there. So I separated them. So here's one of the cosine squared x's. Here's the second. So there were two of them. And then I took this subtracting 2 cos x just to the end. Did that again so I could use an identity and replace this with a 1. And then I rearranged. So here is my 1. There's my 1 at the end. Cos squared x at the front minus 2 cos x I put in the middle. Why? It's like a quadratic. So I factored it because I felt like it. So cos x minus 1 all squared over sine cubed x. And again, if way back here we had simplified this further, our answer at this point would look different. We could even go further with this, but this is where I'm going to leave it, which is one of the challenges with trig. How do you know when to stop? Well, go where your brain takes you, but don't waste too much time, which doesn't help a whole lot, but maybe a little bit. All right, one more example, then check your understanding. We want to find the equation of the line tangent to this function at a point. Similar type of question as we did in chapter 2. So I'll do the quotient rule yet again. Low d high minus high d low, square the bottom, there you go. Notice cos x over sine x, this is a cotangent x. So what we're doing in this question is we're figuring out what's the derivative of cotangent x. What do we get? Well, we have a negative sine times sine, and negative cos times cos. Factor the negative out in front, and have a sine squared x minus cos squared x all over sine squared x. So the derivative of cotangent x is negative cosecant squared x. We'll look at that more in tomorrow's lesson, or the next lesson, whenever it comes. Well, now that we have a derivative, we can figure out a slope when x is pi by 4. So we're going to plug that into this function. So here's what we get. I used this derivative, the 1 over sine squared x, because I'm more comfortable figuring out exact values for the sine function rather than cosecant. So that's what I did here. The negative 1 over sine x all squared. Sine of pi by 4 is root 2 over 2. Or if you use the special triangles, it's just 1 over root 2. Either way, when we simplify it, we get the derivative is equal to negative 2. So that is the slope for the line tangent to this function at the point where x is pi by 4. So then we can take this xy ordered pair, and there we go, we can see it, but I can't see my arrow, so I got to scroll down. We will plug that into the point slope form for the equation of the line. Y minus y1 equals slope times x minus x1. Rearrange, and I put it into general form. There you go. There's a question for you to try. Pause the video at this point. Try question 14. When you've got it worked out, restart the video to see my solution. Here we go. We want horizontal tangent lines, so we want to know where the derivative is equal to 0. When I rearrange it, I get cosine of x equals negative 1/2. Oh no! Math 30-1 again, solving trig equations. Maybe I should have said, hooray! We get to solve trig equations yet again. Here we go. Here we go. Let's look at this angle in standard position. So a couple of ways we could have done this. So if you use the unit circle, then we're just looking to see where do I have an x value of negative 1/2, and we're going to see in the second and the third quadrant. Or you may remember that cosine is x over r. R is never negative, which means x is negative, which gives me a negative 1 here for this triangle. And for this triangle, negative 1 is this horizontal side length. Well, length in the negative direction. And if you use the special triangles, the r value is 2. So those are 2's. And we look and figure out, oh, the reference angle must be a pi by 3. If you wanted to do inverse trig operations, again, what I'd recommend is thinking my reference angle is equal to the inverse cos, of positive 1/2. So don't stick the negative in here. I Depending on the trig function, it gives us solutions in different quadrants. So if we always do the positive, then we know we're getting the reference angle, and we'll use that reference angle to figure out our solutions. And here are my solutions. So this blue angle is 2 pi by 3. So pi minus the pi by 3 gives me this 2 pi by 3. Adding multiples of 2 pi. So again, 2 pi is one period for the circle, or one complete rotation around the circle. So those are all the angles or coterminal with pi, 2 pi by 3. And then similarly, this big green angle, 4 pi by 3. So it's pi up to here, and then another pi by 3. There you have it. Time to practice some questions before we look at more trig functions and their derivatives. Take care.